So in our last lecture, we discussed that there is a tangential velocity which is related to the angular velocity as omega cross r. Agreed? And we saw that if a particle moves in a circular motion, this is the center. So if a particle moves in a circular motion, then there is always a velocity with which the object moves, and that velocity is always tangential to the circle. Okay, tangential at any position is tangential to the circle. This velocity is called as a linear velocity that can be defined as with any number, that is, say this is 5 meter per second or so. Agreed? Now the thing is, we also defined an omega, which is the angular velocity, which is defined in terms of some radian per second, like say pi radian per second or pi by 2 radian per second, whatever. Then we saw that if now what we'll do is, now we'll see what happens when we apply force. So consider this is the circle again. Okay, and now consider there is an object here. So what we have an object at this place. If on this object we apply a force F, what happens? This object, and what is the nature of this force? This force has to be always applied tangential. This force has to be always applied tangential. As a result of which, what will happen to the object? The object will move along the circle with an acceleration now. Okay, that acceleration is say a, and this a is your linear acceleration. So let me write AL. Similarly, this is same to as your straight line motion. So if you have an object here, and if you apply a particular force F on the object, what happens? The object moves with an acceleration A. Similarly, here we have an object on a circular path, and we apply our force in such a way that the object is always kept on that circular path, and now the object is moving on the circular path with an acceleration AL. So AL is called as the linear acceleration. This is same as the acceleration that we see in one-dimensional motion. These are the linear acceleration. And then we learn that not only there is a linear acceleration, which is quite logical, but there is one more acceleration, that is centripetal, that acts towards the center, and that is called as the centripetal acceleration. Now, when we learned that there is a linear acceleration, this linear acceleration was caused because we applied a force, a tangential force, to the object in such a manner that we kept the object moving on the circle. And then I said there is a centripetal acceleration, and then obviously with this acceleration there must be a force that is acting on the object that is moving with an that is moving in circular motion, and this centripetal force acts towards the center, and this centripetal force keeps the object in the circle's circumference. So this is the importance of centripetal force. This force is actually making it go with an acceleration AL, and this force is not at all helping to keep the object on a circular track, but this force, this is the main force that keeps the object on the circular track. Okay, if there were no centripetal force and you apply a linear force on this particle, the green particle will go what? This green particle will go in a straight line. This will go away. This will never move in a circle, because this kind of force always creates a straight line motion. The only reason that the green particle is moving on the circumference on the circle, the only reason it is moving on the circumference of the circle is because there is a centripetal force that acts towards the center, which is always keeping it on the circumference of the circle. So this force is called as the centripetal force. So what was the formula for centripetal force? Was the centripetal acceleration was calculated as what? The centripetal acceleration was omega cross dr by dt. Okay, omega cross dr by dt. And as I mentioned earlier, even though the radius is same, the direction of the radius is changing. So this is not a thing that goes to zero. This has some value, because you see, when you write d by dt of r vector, then you can write what? You can write magnitude of r into direction of r. Now when the object is moving on a circular motion, no doubt the magnitude of r is not changing with time, but the direction of the r is always changing with time. You can look at it. We have already discussed in our last lecture. Agreed? So we can actually write this as omega cross v. Now you'd say, how can I write dr by dt as v? Yes, I can do. Let me explain you why. You see, consider this circle again and look at this. This is a radius vector. Say this is the radius vector RA. Agreed? And this radius vector is acting along this direction. Consider another radius vector very close to RA, and say this radius vector is RB. Okay. Now, can you tell me what is RB minus RA? So what will be the radius, what will be the line that will depict the RB minus RA? That line will be the line that connects these two. Okay. So any change in R, that can be written as RB minus RA. Okay. So this is the vector that represents the delta R. Look at in which direction delta R is acting. Delta R is acting tangential to the circle. So don't you see that the direction of delta R is same as the direction of the velocity, the tangential velocity? Okay. And the moment you do delta R by del t, then it actually depicts what? It actually depicts your tangential velocity. That's why I have proudly written with all confidence that dr by dt is my velocity, because the dr itself is in the direction of velocity. If you take RA and RB very close to each other, so consider another circle. Okay, and in this circle what I want to do is, let me take RA and RB very close to each other. So this is say RA and this is say RB. You see, they're very close to each other. So if they're very close to each other, then in which direction will be RA minus RB? Obviously the line that connects them, and that line is tangential to the circumference of the circle. So you see that the direction of delta R is same as the direction of velocity, the tangential velocity. So what is centripetal acceleration? So centripetal acceleration is omega cross v. Now as I mentioned earlier, whenever you see a cross product, it always represents a general statement. So you can always make it special. Since there is a sine theta here, just assume that sine theta is 1 by taking theta is 90 degrees. So what you are left with? You are left with an omega and v, where you have assumed that the angle between omega and v is taken as 90 degree. This is actually true in 2D circular motion. It is nearly true 95% of the time. This is true. Now what is omega? We know that omega is v by r. Okay, we have removed all the cross product because it is not required. We have assumed that theta is 90 degree. So this is what? This is v square divided by r. So so centripetal acceleration is v square divided by r. Now how to find force? Once you know the acceleration, force can be easily calculated by multiplying mass with acceleration. So what is the mass? Mass is the mass of the ball or the object that is moving on the circle. Agreed? So what happens to here? So the centripetal force is m v square divided by r. It means if you make the object go faster, then you have to put more centripetal force to keep the object on the circular track. And it is this. But is this a true relation? Is this a true relation? The fact is, this is not a true relation. The true relation is when you see why this is not a true relation, because v is also a function of r and r is a function of r. True relation is when I can write the centripetal force equals to some constant into r. So let us see. So this was actually omega v. So there will be another expression, v is equals to omega r. So there will be omega square r. This is actually the true expression of the centripetal force. It means centripetal force is in fact directly proportional to r. It's not inversely proportional. Many people will ask you, is centripetal force inversely proportional to r? You say no, centripetal force is not inversely proportional to r, because in this expression everything is not constant. No doubt m is constant, but velocity is a function of r. Why velocity is a function of r? Because if you calculate the velocity here at the edge and if you calculate the velocity here, they are going to be different. When you look at a fan moving, you see the tip of the fan moves at great velocity, but you observe the objects near the center of the fan, they move with less velocity. So tangential velocity is different at different distance from the center, but the angular velocity is constant. This was the reason why we were bound to define a angular velocity in a circular motion, because in circular motion at different radius the velocity, the tangential velocity is different. Okay, let me explain again. Look at this circle. Okay, so if you have a rod, so consider this is a rod which is moving in circular motion, then you will find that the tip of the rod moves at a higher speed. This tip of the rod has a great velocity, and when you look at this point of the rod, this moves circular, no doubt, but this moves at a velocity, the linear velocity is less. Okay, why? Because v is equals to omega into r. So if the value of r is less, it means if you are looking at objects near the center, then their linear velocity will be less, but the angular velocity will be always same, because all of them, because the entire part of the rod, each point on the rod will cover the same angle in the same time. Agreed? So this is your centripetal force. So we'll discuss more on circular motion, but I think this is the most important lecture where you actually understand the origin of centripetal force. You understood that centripetal force is highly responsible for keeping objects in circular motion, and centripetal force is directly proportional to r. So in the next lecture we'll discuss more.